relationship between the charge density and the field, which we have a relationship between the electric field of potential, and we have a relationship between the potential and the charge density. Now, if I'm given a charge density, one needs to ask oneself, if I want to find the field, what's the best thing to do? That will depend on the circumstance at hand. If I have some symmetry in the problem that allows me to use Gauss's law, well, I should use it. And then if I want to find the potential, it's best to go around things this way. That is to say, I have the charge density, I get the electric field, and then as you suggested, I could just integrate E dot dl to get the potential. So that's if there's symmetry. On the other hand, that's a rare circumstance, and quite often I can't use Gauss's law to simply determine the electric field from the charge distribution. In which case, the better thing to do is to directly integrate the charge distribution with the Green's function. I mean, the solution to Green's function was trivial in this case. So if I'm given some funny charge distribution, like I have charge on a line segment, you know, Gauss's laws are going to do it for me. So I would directly integrate, in that case, to get phi. From the charge distribution. And then take the gradient of that to get the electric field. So how I go around this triangle depends on, you know, typically the symmetries of the problem. So, for example, suppose I have a sphere, or something that's more better looking at this. Trying really hard. Which has a radius r, which has a surface charge density, a uniform surface charge density, total charge Q. And I want to find the electrostatic potential associated with this charge distribution with ground at infinity. So typically, if we have a charge distribution which is in a compact region of space, so it's not like an infinite line charge, then if there is no other grounding surface that is defined, one would take the ground to be at infinity, would just be the natural place to put it. One doesn't have to put it wherever you like, but let's just choose it there because it's the natural thing to do. Okay? So, what do?
You could use Gauss's law and then just integrate.
Exactly. So in this case, I mean, you could look in, I think in Griffiths, it's done. It's a nasty integral to plug in the charge density and integrate it. It's doable. I mean, we could break it up into little rings, right? And we can find the potential associated with each ring and then integrate those rings. I mean, it's a kind of a calculus problem. But it's trivial to do this problem, realizing that we can write down the electric field instantly based on Gauss's law. So because of the symmetry here, we should use Gauss's law. And so, based on that, what is the electric field in this circumstance as a function of position? Well, again, you remember Gauss's law, we write down the form of the electric field being only depending on the distance from the origin and in the radial direction. And of course, from that we know that the surface integral is the electric field times the surface area at that radius, and that equals the enclosed charge at that radius divided by 4 pi r squared times 4 pi. Because this integral is 4 pi times the enclosed charge at that radius, right? So what is the electric field class in this problem? Outside it's q of r squared in the radial direction, for r outside the sphere. Right? So it says if there was a point charge at the origin, there's no difference between if I have the spherical symmetry, and what about for r less than r? 0. Because of the spherical symmetry. Okay? If I didn't have spherical symmetry, you know, if I have a ellipse charge, and I ask what is on the surface of the ellipse, and I ask what's the electric field inside this, it's a rookie mistake to say it's 0, because charge enclosed inside is 0. But that's not true, because I can't factor out the electric field from the surface there. Okay? It was only because we were allowed to factor it out based on the symmetry that we were to say the integral has to be 0 if charge enclosed is 0, but it doesn't mean the electric field is 0. It just means the surface integral is 0. Okay? Rookie mistake, don't be a rookie. That'll be our motto. So, right, so then the potential is also spherically symmetric. The equipotential surfaces are spheres, so it only depends on the radial distance, and that's the integral from ground, which is at r equals infinity, up to r, doing my, so ground, here's infinity, if you ever wondered what infinity looked like, there it is. And then we're coming in to whatever radius r along the radial line segment. Okay? And so that's equal to the, well, it sort of depends whether my r is inside or outside this shell. If r is bigger than the radius of the sphere, the electric field is the point charge electric field. We should make that a dummy integral, a dummy variable, call it prime. And for our inside the sphere, well, I have to break up the integral into two pieces because the electric field is different up to the radius of the sphere, it's that, but then inside, it's 0. Right? And this is Q over R. So, in this circumstance, just to remind you, this is quite a simple problem. I'm sure you've seen in your freshman physics. The electric field in this problem is 0 and then falls off like 1 over r squared. There is a discontinuity here. The electric field at this point is Q over r squared. And there is a discontinuity here in the electric field at the radius of the sphere. And that discontinuity is associated with the fact that there's surface charge density at that radius. And so, as you're seeing your homework, you're reminding yourselves of this in problem 3 of the assignment this week. If I have charge that is concentrated onto a surface, then the electric field is discontinuous across that surface. The component of the field perpendicular to the surface, normal to the surface, inside the surface at the radius is 4 pi times the surface charge density, which is 4 pi times Q over 4 pi r squared, or Q over r squared. Right? Inside is 0, outside it's this. Okay, and the potential thus is constant inside the sphere. And then falls off. All right? Okay. So, now of course, an important concept in thinking about the electrostatic potential, let's just throw on the lights here, excuse me. Is the notion of work and energy in electrostatics. So, if we have some source which is producing some electric field, whatever this is. So this is the electric field from some source. Okay, and now I have there is some charge Q here, and I want to move this charge from point A to point B. Then I have to do work to do that. Okay? And if the work I do is applying a force through a distance, that force that I'm going to apply is going to be equal and opposite to the force acting on the charge by the field. So the work I do against force of the electric field, and that force is Q times E, right? It's the local force on the charge. So the work I do, yes I do, is minus the, I'm applying the force equal and opposite. So that's minus Q E dot dl, XA, XB, which is Q times the gradient of the potential, electrostatic potential, which is thus equal to Q phi at XB minus Q phi at XA. Okay? So the work I do is when we move the charge against the field is then said to be put into the potential energy so the work I do moving this thing uphill is the potential energy in the charge. Okay? So that's why we define this as minus the gradient, because we want it to be the fact that the potential energy is positive when I do work against the force. That's why where that minus the gradient comes from. So the potential energy, so in an external field, a charge in an external field so there's some source that produces field. I want to know what's the potential energy is the charge times the local electrostatic potential. Okay, so the change in potential energy is the work I do, going from A to B. So of course, the units of electrostatic potential are energy per charge. SI units, that's joules per coulomb. In Gaussian, it's something crazy like stat volts per ESU. No, actually, yeah, that's right. Or ergs. Erg. Okay. All right, so that's one important notion of work and energy in electrostatics. This is the potential energy. Oh, by the way, of course, if we had a collection of charges, then we would just sum that, and if we turn that into a continuum, if we have a charge distribution rho, then we would say this would be the integral of the dq's, which is rho times the volume element times the potential. Okay? Again, this is the potential energy of a charge distribution in an external field. Now there's a slightly different concept, and a very important concept in electromagnetism, which is the work necessary to establish a charge distribution. So what do I mean by this? Well, let's think, just to start, let's think about some collection of point charges. Sitting around somehow. So in order to establish this charge distribution, well, I can imagine initially all of the charges infinitely separated. So they don't feel each other's presence. And then I bring in each charge from infinity one at a time. Okay, I didn't have to do any work to do that. I just had to make a funny noise. Didn't cost me anything except my humility, and which I don't have much of anyway, so I didn't lose anything. And we put that charge there. Of course, this charge now produces an electric field, so the next charge, doing work against the force, and I bring it in over here, right? So at this point, so for charge 1, no cost, no work. Simple as pie. Charge 2, well, the work I did was the potential energy of this charge in the presence of the electric field produced by that charge. And we just said what that was. So the work that charge 2 has to do Q2 times the electrostatic potential produced by this external field. And what is that? What's that potential? Q1 over the distance between the source and the observation. In this case, the observation is, so this then is equal to Q1 times x2 minus x1, right? That's the potential seeing that position x2 with the charge at x1. Okay, here comes charge 3. Now, charge 3 has to push against the field of these guys, right? So I got charge 3 times Q1 over X3 minus X1 plus Q3 times Q2 X3 minus X2, etc., etc., etc. So, what we learned from this is that the work I do to move these charges in from infinity and position them at whatever positions, their final positions, this is what we call the potential energy of the configuration of charges, is equal to, well, I got the sum over all pairs, the charge Q sub I, Q sub J, over Xi minus Xj, magnitude, sum over all I and j, I not equal to j. Of course, if I do this, I would double count, right? Because I sum over both I and j, I'll have a Q1 times a Q2, but then I'll have a Q times a Q1. And I only have one such term. So to do this, to avoid the double counting, I should put in a factor of half. Okay? And this factor of a half is important. It distinguishes the potential energy of the configuration versus somehow there was some other work that was done to establish all the other charges. Maybe, you know, there was a battery that put in, and then they talk about the last charge. This is bringing everything in, all the charges. See here, I didn't take into account the energy of the sources. So, notice you can rewrite this in another way. Let's move it up here. This is equal to 1/2 the sum over I not equal to J Q sub I sum over J. Well, let's do this one. Sum over I sum over J not equal to I Q J X I minus xj. And what is this? This is equal to the potential associated with all the other charges. This is the electrostatic potential. Associated with all other charges other than I, with ground at infinity. So I can write this as sum over I, Qi, the potential at I, no self-energy. Okay, that was sort of implicit in this, the fact that it took no work to bring the point and charge in, the original one. So we didn't count the force against itself. Okay, so notice here, important thing here, or I can write this for a continuum. So notice the difference between this formula and this formula. What's the difference? A factor of 1/2. Okay, so this is a different situation in which there are electric fields produced by some source, and now we're asking what is the potential energy of some other charge in that external field. Whereas this problem is how much energy it was to create the charge distribution itself. Right. So we now there is a very important way of thinking about this energy of configuration. So of course, note that rho is equal to 1/4 pi times the divergence by Gauss's law. So whatever the local divergence of the electric field is, tells me what the local charge density is. So I can re-express my potential energy of the configuration in terms of just the field and the potential itself rather than the charge distribution. now we use the famous trick of integration by parts. And as we discussed at the problem session last time, integration by parts basically means take the derivative of one term and throw it onto the other term and put a minus sign on it. And we see that explicitly by noting that the derivative of the product, in this case the divergence of the field that I get when I multiply the scalar potential by the electric field. How do I do this dot product? Well, I don't have the inside cover of Griffiths with me. I use my tensor notation. This is partial I 5x e sub I. And then I use the product rule, the derivative of the product, take the first times the derivative of the second, plus the second times the derivative of the first, right? And this sum over I means the divergence of E. And this is E dotted into del on phi. Right? So what we see then is that del dot E times potential is equal to the divergence of phi times E minus E dot grad phi. Just solving this, moving this to the other side of the equation. So far, so good? All right, so what we now have is the potential energy of the configuration is, this is of course the integral over all space. Plugging in over here, we got 1 over 8 pi times x times minus the gradient of phi, or put a minus sign out there, E dotted into grad phi, now, plus 1 over 8 pi, the integral v cubed x, the divergence of E times phi. Using the expression we just had. Now, minus grad phi is the electric field. So this term is 1 over 8 pi, integral over all space, E dot E. This term, well, this, based on the divergence theorem, the integral over a volume of the divergence is equal to the flux of the antiderivative through a surface. These are, in integration by parts, this is what we call the surface terms, for obvious reasons. So here we assume that we're integrating over all space. The surface terms are such that the combination of E and phi falls off faster than the surface area grows, so that at infinity, this is 0. So there's no, the surface term vanishes. And we get a beautiful expression that everyone knows and loves. Maybe not with an 8 pi, but you'll learn to love your 8 pi and eat it too. I might. Is that the potential energy associated with establishing this charge distribution can be thought about equivalently as energy stored in the electric field. So, when I'm pushing those charges together, that potential energy is stored somewhere. It's stored in the field. And the field is thus given a more tangible existence as an entity that's got stuff like energy. We'll see it also as momentum, angular momentum, in some cases. All right, so for example, if we go back to the problem that we were discussing at the beginning of the lecture, the problem of the charge sphere, or the shell, spherical shell of charge, which we have over there. We have two different ways in which we might calculate. The question is, what is the energy necessary to take the charge in from infinity and put it onto that surface? Well, we have two different choices. One way we can calculate it is based on that expression. We know the charge distribution everywhere, and we calculated over there the potential everywhere. Now, in this case, the charge density is 0 everywhere except on the surface, right? So, in this particular case, well, I can rewrite this as integral over the area, the surface charge density on the surface times the potential on the surface. Right? You can always take a volume density times a volume element and turn it into a surface density times a surface element. But the surface charge density is constant, and this is uniform. So this is equal to 1/2 the area times the surface charge density times the potential at the radius r. Okay? And in this case, this is equal to Q over 4 pi r squared. It's Q over the area in this case, because it's uniform. We said it had a total charge Q. And the potential, we said was Q over r at the surface. That's what we got somewhere. So this is equal to, this energy is Q squared over 2r. So I just want to emphasize one tiny little point, because it's always important to check units, okay? And there's often a confusion between the electrostatic potential and potential energy. You see, the potential energy is Q times volts, or Q times the electrostatic potential. So it's got to have a Q squared if it's a potential energy over R. Okay, so this is one way to calculate it. Alternatively, if all our fancy integration by parts wasn't some big wool over your eyes, then we should equivalently be able to calculate this in terms of the integral over all space of the electric field associated with that distribution of charge. Okay? And the electric field in this case is given as it's the field of a point charge outside the sphere, and it's 0 inside the sphere. So we should write this in terms of this integral over spherical shells. So my volume element will be 4 pi r squared dr. That's surface area dr. Little surface, those are my dq dart. The electric field at that r squared. And the electric field is only non-zero outside the sphere. Inside the sphere, the electric field is 0. And we said that outside the sphere, the electric field is the electric field associated with the point charge, which is Q over R squared. So, put it all together, what do you got? 4 pi, 8 pi, a half, the integral, we got a Q squared, we got infinity, I got an r to the 4th dr over r squared, which is Q squared. All right? Now, we have one little paradox to confront. So, note for a distribution of point charges, we wrote this configuration energy like that, right? But on the other hand, we just said that we can also write this as the integral over all space of the square of the electric field. Now, this is always positive, right? Because the square of the field is a positive number. And then we integrate over positive volume elements, so it's positive. Whereas this could be positive or negative. So what the heck happened? Yeah.
Well, so isn't it all like just kind of shifting your baseline, like where your zero of?
Well, it's a good point. I mean, there is a question of, did we somehow choose, I mean, at the end of the day, what's important is the relative potential, because that's what determines the forces, and that's ultimately what we measure. But that's really not the whole story here. Because in fact, notice here that if I shrunk the radius of the sphere to 0, this would be infinity. The reason that this formula is different from this is this formula came from the continuum. In fact, if I were to calculate the potential energy of the configuration, suppose I have a single point charge. Well, the electric field is Q over R squared. And if I were to integrate this over all space, I get infinity. The point is that the expression derived here includes the self-energy of the charge. If it's spread out in a finite volume of sufficiently smeared out like peanut butter, then that's fine. But if we try to concentrate it all the way back down to a point, that would take an infinite amount of energy. And, you know, that reflects itself. I mean, it comes down to many paradoxes in classical EM about how we take into account self-energy of points. And ultimately, that these issues reappear when we start thinking about quantum electrodynamics and quantum QED and what self-energy there are in point charge, the whole question about renormalization of field theories and so forth and so on. The self-energy is an important concept. So, for example, in your homework, you will find there is a problem. If you try to just use the electric field to calculate what the energy stored in that configuration, you'll find that it's infinity because there's a point charge in there, and if you don't, you can't use this formula if you have point charges. Okay. Very good. All right. So, now there's one last important concept that we want to talk about. We're going to talk about in some amount of detail throughout the semester, thinking about macroscopic materials and their electromagnetic properties. And loosely speaking, we divide up in terms of electrostatics. We divide up these materials into two classes, the conductors and the insulators. So, materials really divide fairly cleanly against these two classes. Not exactly, but pretty darn. There are materials that are essentially perfect conductors, like, you know, copper or silver, gold. You know, essentially perfect insulators, wood, rubber, glass. Having to do with whether or not the charges inside those materials are mobile and free to move in the presence of external electric fields, or whether they're tightly bound to the nuclei or the cores in the material. Okay? So when we talk about, and quite often in talking about electrostatics, conducting surfaces are an extremely important concept to include. And so let me just quickly remind you of just a few things about conductors. So if I put a conductor, so here's some chunk of copper, and I put it in the presence of an external electric field. Well then, what's going to happen, of course, is all the mobile negative charges move in one direction, and all the holes move in the other direction with the electric field. You know, one of my other pet peeves, you don't have a lot of pet peeves, but one of